Georg Cantor's first proof of uncountability demonstrates that the set of all real numbers is uncountably, rather than countably, infinite. This proof differs from the more familiar proof that uses his diagonal argument. Cantor's first uncountability proof was published in 1874, in an article that also contains a proof that the set of real algebraic numbers is countable, and a proof of the existence of transcendental numbers. 2 points about which not all authors writing about Cantor's article have agreed are these. Is Cantor's proof of the existence of transcendental numbers constructive or non-constructive? Why did Cantor emphasize the countability of the real algebraic numbers rather than the uncountability of the real numbers? In 1891, Cantor published his diagonal argument, which produces an uncountability proof that is generally considered simpler and more elegant than his first proof. Both uncountability proofs contain ideas that can be used elsewhere. The diagonal argument is a general technique that is useful in mathematical logic and theoretical computer science, while Cantor's first uncountability proof can be generalized to any ordered set with the same ordered properties as the real numbers. The article. Cantor's article begins with a discussion of the real algebraic numbers, and a statement of his first theorem. The collection of real algebraic numbers can be put into one-to-one correspondence with the collection of positive integers. Cantor restates this theorem in terms more familiar to mathematicians of his time. The collection of real algebraic numbers can be written as an infinite sequence in which each number appears only once. Next, Cantor states his second theorem. Given any sequence of real numbers x1, x2, x3, and any interval a, b, one can determine numbers in a, b that are not contained in the given sequence. Cantor observes that combining his two theorems yields a new proof of the theorem. Every interval a, b contains infinitely many transcendental numbers. This theorem was first proved by Joseph Liouville. He then remarks that his second theorem is the reason why collections of real numbers forming a so-called continuum cannot correspond one-to-one with the collection of all positive integers. Thus I have found the clear difference between a so-called continuum and a collection like the totality of real algebraic numbers. The first half of this remark is Cantor's uncountability theorem. Cantor does not explicitly prove this theorem, which follows easily from his second theorem. To prove it, use proof by contradiction. Assume that the interval a, b can be put into one-to-one correspondence with the set of positive integers, or equivalently, the real numbers in a, b can be written as a sequence in which each real number appears only once. Applying Cantor's second theorem to this sequence, an a, b produces a real number in a, b that does not belong to the sequence. This contradicts our original assumption, and proves the uncountability theorem. Cantor's second theorem is constructive and thereby separates the constructive content of his work from the proof by contradiction needed to establish uncountability. The proofs. To prove that the set of real algebraic numbers is countable, Cantor starts by defining the height of a polynomial of degree n to be n-1 plus a0 plus a1 plus and where a0, a1, and are the coefficients of the polynomial. Then Cantor orders the polynomials by their height, and orders the real roots of polynomials of the same height by numeric order. Since there are only a finite number of roots of polynomials of a given height, Cantor's orderings put the real algebraic numbers into a sequence. Next, Cantor proves his second theorem. Given any sequence of real numbers x1, x2, x3, and any interval a, b, one can determine a number in a, b that is not contained in the given sequence. To find such a number, Cantor builds two sequences of real numbers as follows. Find the first two numbers of the given sequence x1, x2, x3 that belong to the interior of the interval a, b. Designate the smaller of these two numbers by a1, and the larger by b1. Similarly, find the first two numbers of the given sequence belonging to the interior of the interval a1, b1. Designate the smaller by a2 and the larger by b2. Continuing this procedure generates a sequence of intervals a1, b1, a2, b2, such that each interval in the sequence contains all succeeding intervals. This implies the sequence A1, A2, A3 is increasing, the sequence B1, B2, B3 is decreasing, and every member of the first sequence is smaller than every member of the second sequence. Cantor now breaks the proof into two cases. Either the number of intervals generated is finite or infinite. If finite, let Bn be the last interval. If the number of intervals is infinite, let infinity equals lim infinitian. At this point, Cantor could finish his proof by noting that infinity is not contained in the given sequence, since for every n, infinity belongs to the interior of Bn, but Xn does not. Instead, Cantor analyzes the situation further. He lets B infinity equals lim infinity Bn, and then breaks the proof into two cases. A infinity equals B infinity and A infinity less than B infinity. In the first case, as mentioned above, A infinity is not contained in the given sequence. In the second case, any real number in A infinity, B infinity, is not contained in the given sequence. Cantor observes that the sequence of real algebraic numbers falls into the first case, thus indicating how his proof handles this particular sequence. Constructive or non-constructive nature of Cantor's proof of the existence of transcendentals. Some mathematicians claim that Cantor's proof of the existence of transcendental numbers is constructive, that is, it provides a method of constructing a transcendental number. For example, Irving Kaplinsky writes, "It is often said that Cantor's proof is not constructive, and so does not yield a tangible transcendental number. This remark is not justified. If we set up a definite listing of all algebraic numbers, and then apply the diagonal procedure, we get a perfectly definite transcendental number." Other mathematicians claim that Cantor's proof is non-constructive. According to Ian Stewart, the set of real numbers is uncountable. There is an infinity bigger than the infinity of natural numbers. The proof is highly original. Roughly, the idea is to assume that the rails are countable, and argue for a contradiction. Building on this, Cantor was able to give a dramatic proof that transcendental numbers must exist. Cantor showed that the set of algebraic numbers is countable. Since the full set of rails is uncountable, there must exist numbers that are not algebraic. End of proof. Collapse of audience in incredulity. In fact, Cantor's argument shows more. It shows that there must be uncountably many transcendentals. There are more transcendental numbers than algebraic ones, and you can prove it without ever exhibiting a single example of either. The above quotations show that these two groups of mathematicians are discussing different but related proofs. One proof is constructive while the other is non-constructive. Both proofs use a construction that takes a sequence of real numbers and produces a real number not belonging to this sequence. This construction is either the one in Cantor's 1874 article, or it uses his diagonal method. The proofs differ in how they use this construction. The constructive proof applies it to the sequence of real algebraic numbers, thus producing a transcendental number. Cantor gave this proof in his article. The non-constructive proof starts by assuming that the set of real numbers is countable, or equivalently, the real numbers can be written as a sequence. Applying the construction to this sequence produces a real number not in the sequence, which contradicts the assumption that this sequence contains all real numbers. Hence, the set of real numbers is uncountable. Since the set of algebraic numbers is countable, transcendental numbers must exist. This proof does not construct a single transcendental number. Cantor's constructions have been used to write computer programs that generate transcendental numbers. These programs show that his constructions produce computable numbers. The program that uses Cantor's diagonal method computes the digits of a transcendental number in polynomial time, while the program that uses his 1874 construction requires at least sub-exponential time. The constructive nature of Cantor's work is easily demonstrated by using his two methods to produce irrational numbers. Both constructions start with the same sequence of rational numbers between 0 and 1. This sequence is formed by ordering these rational numbers by increasing denominators, and ordering those with the same denominator by increasing numerators. The table below constructs an irrational number x by using Cantor's diagonal method. The strategy is to construct the decimal representation of a number that differs from the decimal representation of every rational number in the sequence. We choose the nth digit of x so that it differs from the nth digit of the nth member of the sequence. If the latter digit is between 0 and 7, add 1 to obtain the nth digit of x, otherwise, let the nth digit of x be 0. So the decimal representation for x differs from every decimal in the sequence. Also, x is between 0 and 1, and its decimal representation does not contain the digit 9. Hence, x is irrational. The next table constructs an irrational number by using Cantor's 1874 construction. The strategy is to construct a sequence of nested intervals such that every rational number is excluded from the interior of some interval. Cantor's construction starts by finding the first two numbers in the sequence that belong to the interior of the starting interval 0, 1. These numbers are 1/2 and 1/3, and they form the interval 1/3, 1/2. Next we find the next two numbers in the sequence that belong to the interior of 1/3, 1/2. Continuing this process generates a sequence of nested intervals. This sequence does not terminate since we can always find two rational numbers belonging to the interior of an interval. In the table, the first column contains the interval, and the last column lists the rationals excluded in the search for the first two rationals belonging to this interval's interior. These excluded rationals are in the same order as the original sequence with one exception, namely, one of the endpoints of the next interval. For example, the exception in the first row is 2/5, and it is the first number excluded in the next row. Every rational number is excluded from some interval's interior because the sequence of intervals does not terminate, and the interior of every interval excludes at least two rational numbers. Thus, a real number belonging to the interior of every interval is irrational. In his proof, Cantor constructs such a real number by taking the limits of the endpoints of the intervals. The development of Cantor's ideas. The development leading to Cantor's article appears in the correspondence between Cantor and his fellow mathematician Richard Dedekind. On November 29, 1873, Cantor asked Dedekind whether the collection of positive integers and the collection of positive real numbers can be corresponded so that each individual of one collection corresponds to one and only one of the other. Cantor added that collections having such a correspondence include the collection of positive rational numbers, and collections of the form where n1, n2, n-nu, and nu are positive integers. Dedekind replied that he was unable to answer Cantor's question, and said that it did not deserve too much effort because it has no particular practical interest. Dedekind also sent Cantor a proof that the set of algebraic numbers is countable. On December 2, Cantor pointed out that his question does have interest. It would be nice if it could be answered, for example, provided that it could be answered no. One would have a new proof of Liouville's theorem that there are transcendental numbers. On December 7, Cantor sent Dedekind an intricate proof by contradiction that the set of real numbers is uncountable. This proof uses infinitely many sequences of real numbers, while the published proof uses only two sequences. Taken together, the letters of December 2 and 7 provide a non-constructive proof of the existence of transcendental numbers. On December 9, Cantor announced the theorem that allows him to construct transcendental numbers as well as prove the uncountability of the set of real numbers. I show directly that if I start with a sequence omega-1, omega-2, omega-n, I can determine, in every given interval alpha, beta, a number eta that is not included in. This theorem is the second theorem in Cantor's article. After the publication, Dedekind wrote some personal notes about the correspondence, in which he pointed out that the proofs in the Cantor's article were taken from letters he had sent to Cantor. The mathematical historian José Ferreiros states, according to Dedekind, Cantor's paper, 1874, was based on a transcription of two of his letters, one written on November 30 or December 1, the other on December 8, 1873, both of which are now lost. In his personal notes, Dedekind wrote, after a short time, this theorem and its proof were reproduced almost literally, including the use of the technical term, height, Hoa, in Cantor's article. Why Cantor's article emphasizes the countability of the algebraic numbers. During the Christmas holidays, Cantor visited Berlin and showed his work to his former professor Karl Weierstrass. On December 25, Cantor wrote to Dedekind about his decision to publish. Although I did not yet wish to publish the subject I recently for the first time discussed with you, I have nevertheless unexpectedly been caused to do so. I communicated my results to Mr. Weierstrass on the 22nd. On the 23rd I had the pleasure of a visit from him, at which I could communicate the proofs to him. He was of the opinion that I must publish the thing at least insofar as it concerns the algebraic numbers. So I wrote a short paper with the title, On a Property of the Set of Real Algebraic Numbers, and sent it to Professor Borchardt to be considered for the Journal für Mathe, Krell's Journal. In a letter to Philip Jourdain, Cantor provided more details of Weierstrass' reaction. With Mr. Weierstrass I had good relations. Of the conception of enumerability, countability, of which he heard from me at Berlin on Christmas holidays 1873, he became at first quite amazed. But, after 1 or 2 days passed over, it became his own and helped him to an unexpected development of his wonderful theory of functions. Weierstrass probably urged Cantor to publish because he found the countability of the set of algebraic numbers both surprising and useful. On December 27, Cantor told Dedekind more about his article, and mentioned its quick acceptance. The restriction which I have imposed on the published version of my investigations is caused in part by local Berlin circumstances and in part because I believe that it is important to apply my ideas at first to a single case. As Mr. Borchardt has already responded to me today, he will have the kindness to include this article soon in the Math Journal. Cantor gave 2 reasons for restricting his article: local circumstances, and the importance of applying my ideas at first to a single case. Cantor never told Dedekind what the local circumstances were. This has led to a controversy. Who influenced Cantor so that his article emphasizes the countability of the set of algebraic numbers rather than the uncountability of the set of real numbers? This controversy is also fueled by Cantor's earlier letters, which indicate that he was most interested in the set of real numbers. Cantor biographer Joseph Dorban argues that local circumstances refers to the influence of Leopold Kronecker, Weierstrass' colleague at the University of Berlin. Dorban states that publishing in Krell's journal could be difficult because Kronecker, a member of the journal's editorial board, had a restricted view of what was acceptable in mathematics. Dorban argues that to avoid publication problems, Cantor wrote his article to emphasize the countability of the set of real algebraic numbers. Dorban uses examples from Cantor's article to show Kronecker's influence. For example, Cantor did not prove the existence of the limits used in the proof of his second theorem. Cantor did this despite using Dedekind's version of the proof. In his private notes, Dedekind wrote, My version is carried over almost word for word in Cantor's article. Of course, my use of the principle of continuity is avoided at the relevant place. The principle of continuity requires a general theory of the irrationals, such as Cantor's or Dedekind's construction of the real numbers from the rationals. Kronecker accepted neither theory. In his History of Set Theory, José Ferreiros analyzes the situation in Berlin and arrives at a different conclusion. Ferreiros emphasizes Weierstrass' influence. Weierstrass was interested in the countability of the set of real algebraic numbers because he could use it to build interesting functions. Also, Ferreiros suspects that in 1873 Weierstrass might not have accepted the idea that infinite sets can have different sizes. The following year, Weierstrass stated that two infinitely great magnitudes are not comparable and can always be regarded as equal. Weierstrass' opinion on infinite sets may have led him to advise Cantor to omit his remark on the essential difference between the collections of real numbers and real algebraic numbers. Cantor mentions Weierstrass' advice in his December 27 letter. The remark on the essential difference of the collections, which I could have very well included, was omitted on the advice of Mr. Weierstrass, but he also advised that I could add it later as a marginal note during proofreading. Ferreiros' strongest statement about the local circumstances mentions both Kronecker and Weierstrass. Had Cantor emphasized it, the uncountability result, as he had in the correspondence with Dedekind, there is no doubt that Kronecker and Weierstrass would have reacted negatively. Ferreiros also mentions another aspect of the local situation. Cantor, thinking of his future career in mathematics, desired to maintain good relations with the Berlin mathematicians. This desire could have motivated Cantor to create an article that appealed to Weierstrass' interests, and did not antagonize Kronecker.